Let's look at another example of an optimization problem. Let's now find the absolute minimum of xy plus 3y squared, subject to the constraints that xy squared equals 12 and that we want y to be positive. So the function that we're trying to maximize or minimize, remember that's what we call the objective function. It really is your objective to get this as big or as small as possible. And well, in this case we kind of called out the constraint already. The constraint is given by an equation that relates your inputs. And then sometimes you have some other side conditions like bounds for some of the variables. So remember that our first step is to solve the constraint for one of those variables. And you can choose to solve it for whichever of those seems more convenient. So in this case, we could either use that x is 12 over y squared, or we could try to solve for y, in which case we get y squared is 12 over x. So y is, well, normally it'd be the plus or minus the square root of 12 over x, but since y is positive, we know that it must be the positive square root. So you can really use either of these that you want to, but it's in your best interest to pick the one that looks simpler. So I'm going to avoid using the square root one because that one's just a little bit ugly. So let's think of it as x is 12 over y squared. Then we're going to take what we found and plug into the objective function. So what do we have? We have xy plus 3y squared, and x is 12 over y squared. And then you just simplify that. And so we end up with 12 over y plus 3y squared. And we'll call that f of y. So that's the single variable function that we want to, in this case, find the minimum of. Now, last time we looked at an example where you had a closed bounded interval of possible x values. And so the question is, well, what y values am I allowed to consider here? Well, so far it looks like the only restriction we have is that y has to be greater than 0. So I want to find the minimum of f on the range where y is in, well, it's in the interval between 0 and infinity. So this is a little different than what we saw before. What I'm going to do is just defer for a minute, thinking too hard about this, and we'll just look at the critical point, and then I'll kind of come back and justify why what we do works. So let's go ahead and just find the critical points. So f prime in this case is negative 12 over y squared plus 6y. We're going to set that equal to 0 and solve. I should actually be a little bit careful and make sure that there aren't any y values that make f prime undefined, because of course y equals 0 will make it undefined. But since we're considering y values that are greater than 0, other than that, f prime is defined everywhere. So if we just add 12 over y squared to both sides, get 6y is 12 over y squared. And then if I multiply both sides by y squared and divide both sides by 6, you get that y cubed is 2. And so y is the cube root of 2. Okay, so we have a single critical point. Now what we're going to do is actually classify that critical point using the first derivative test. So remember, this is where we put down a number line with the critical point on it. And remember, we're only looking at values that start at 0. In fact, 0 is not even allowed, but anything greater than 0 is fine. So these are the y values. And we plug them into f prime. So between 0 and the cube root of 2, well, 1, for example, is in between those. And f prime of 1 is a negative value. So that means that f is decreasing for the first half. And then if you take f prime of some positive value, could be 10, for example, well, you have negative 12 over 100 plus 60, which is clearly greater than 0. It's something positive. So the critical point that we've found is a local minimum. Now that's great, but what we really want is to find the absolute minimum of f on this unbounded range from 0 to infinity. And so here's the sort of best part. We're going to argue that this local minimum really is a global minimum. So notice that f is continuous on this range from 0 to infinity. Let me just go back to f and remind you what that actually was. So f was this function 12 over y plus 3y squared. The only discontinuity is at y equals 0, and we're kind of avoiding that by staying just to the right of it. So we have a continuous function on this range from 0 to infinity, and we have a single local minimum. And so the conclusion is going to be that that local minimum must be an absolute minimum. And let me just kind of try to convince you via a picture, more or less, for starters. So imagine you have a graph. I have a local minimum here, so something like this. And in fact, what we saw was that the graph is decreasing for the entire time up to that local minimum. Now, if we had discontinuities, you can do some sort of shenanigans that would get you points that are maybe lower than this local minimum. So, for example, you could have a graph that is, say, decreasing, 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 and then has a sudden jump, and then starts decreasing again. But okay, I've ruled out jumps, and I've ruled out vertical asymptotes and all that kind of thing. So I can't have any kind of sudden skips here. So it's just going to be decreasing, decreasing, decreasing until it hits the minimum, and then start increasing again. Well, I mean, that's just it. There's no way to get any lower than that local minimum without doing some kind of discontinuity. So it turns out that in this case, since f is continuous and we have a single local minimum, well, that implies that the local minimum is an absolute minimum. And that's a pretty common feature of these problems, that you'll end up having an unbounded interval. So in other words, there's no hard cap on how high y can get. But typically those functions will then be continuous on that interval, and so then as long as it has only a single local minimum, then that's going to be your absolute minimum. Or if it has a single local maximum, then that will be your absolute maximum. Okay, so finally let's actually answer the question. I have to be a little bit careful because exactly what is asked can differ from problem to problem. So let's go back up to the question. It said we want to find the minimum of this function. Xy plus 3y squared, remember, just became 12 over y plus 3y squared. So maybe copy this down here. We found that the minimum happens when y is the cube root of 2, and so now we just want to plug that in. So the absolute minimum is f of the cube root of 2. So it's 12 over the cube root of 2 plus 3 times the cube root of 2 squared. And you could simplify that sum, but that's essentially what the answer is.